Hello, everybody, and thank you for the organizers to give me the opportunity to show you some work of the few last years. So my topic today will be the northern part of the Tibetan Plateau and this junction between the Altyn Tagh Fort and the Haiyuan Fort through the Qilian Shan ranges. What you see here is a view of the Danghenan Shan that we visited in 1996. It was during my PhD. It was one of the Altyn Tagh Fort field trips that we did with Xu Shiwei, Paul, Rick Ryerson, and Bertrand Meyer. And the work part of the work I will present today is done with Yangshu Shao, who revisited a bunch of the sites that we visited in the late 90s and beginning of the 2000s, and to add more data and to sometimes reinterpret the sites. Okay, so here are some of the data and the papers from which I will present you the data later on. It's just also the opportunity so you can see that there are much more co-authors on this work. I notice also, I want to notice in particular on the Haiyuan Fort here, Rémi Matreau and Jan Klinger, where we worked on the Eastern Haiyuan Fort. I will show you later on. So some souvenirs here. So this was 1996, probably in Dunhuang or in Soubei, I don't remember, in front of the hotel with Bertrand, Rick, and Paul. These are our two famous cars here, Beijing Jeep to the left and the Toyota to the right. These cars, I think we used them during, I think maybe more than 10 years in this area. This is a view of the team with Xu Shiwei in the middle here in front of the Danghenan Shan, one of the glaciers. We're about 5,000. We are at about 5,000 meters elevation here. It was in the spring, so this was in June. Well, in June it's snowing sometime on the plateau here in the Yanshiwan basin. So, voilà. So this is what I want to address. In fact, we talked about extrusion yesterday. Well, extrusion looks also like that. This left lateral present-day extrusion, at least, the northern boundary of it is this left lateral strike-slip system or fault zone that runs for about almost 4,000 kilometers from the western Pamir to the east of China. And so there is a junction between the Altyn Tagh Fort and the Qilian Shan. The Altyn Tagh Fort, as we saw earlier, has its slip rate that becomes smaller as you move to the northeast. But displacement or strain is not vanishing. It's just transferred through this big step over, which are the Qilian Shan, which accommodate literally shortening, but not only shortening, it's also left lateral strike slip faulting at places. This is another view, a map that was published in the famous paper by Bertrand Meyer and co-authors. And as you can see here, it's maybe clear. Well, I hope it comes up. Well, maybe it's a little bit clearer. You see the Altyn Tagh Fort that propagates to the northeast, that branches into these thrust forts, which again branch again on the Haiyuan Fort here in the Danghenan Shan, and then allowing again the Haiyuan Fort to take strain and increase its slip rate towards its central part. Okay, so now I will more focus on this part. we will first look at some sites along the Haiyuan Fault here on the east, and then I will come back along the Altyn Tagh Fault. Again, here another map where things are a little bit more clear, probably. Okay. Let me just continue right away. So this is the same map here with the GPS strain field that you have already seen. So what you see here on the top is the geological slip rates that are determined along the Altyn Tagh Fault in this part where it passes this junction here near Supei. I will come back to that later on, which at Supei, you have this Danghenan Shan range that branches into the Altyn Tagh Fault. And you can see here that, well, there is still, and I guess it's the fate of these geological rates. They are different and they have some error bars for different reasons. But we probably go here from about 10, 11 millimeters per year towards 4 or 5 millimeters towards the east past this junction. And on the Haiyuan Fault, again, you can see that the geological slip rates have they're noisy. This pinkish or orange shading here is just to show that maybe there are some common values here. So the idea here is that only few points on the west along the Haiyuan Fault here, but the idea is that the fault pick up some slip rate or some strain coming from these ranges to the north, and then has probably a high slip rate around 8 to 10 millimeters per year in this part here in the Lenglong and west of the Lenglong, and then has a rate around 6 to 7 millimeters per year as you move towards the east, and a rate that almost diminishes towards zero as the fault approaches or enters into the Liupan Shan here in the east. So if I just go back, this is what I wanted to say somewhere here. Okay, and so what you see here is that the Haiyuan Fault is somehow colliding with the Ordos block here. So the slip rate on the fault maybe vanishes and becomes almost zero, which doesn't mean that extrusion stops here. It's just that deformation is towards the north of the fault. Rotation and extension along the Ordos is taking up probably some of the eastward displacement. Okay. So if we look at now shortening across the Qilian Shan, this is a compilation here published by Xu and co-authors. It's a section that goes from south to north here. From north to south, from the Hoshi corridor to the Chayam Basin. And what you see here is that the GPS data is showing about on average 6 millimeters per year of shortening over this 340 kilometer long pass, and probably taken up by these different mountain ranges. The precise amount that is accommodated by each of these ranges, I think, cannot be clearly defined with this data. Maybe we can do better with the INSAR data, or maybe we should combine all these. And it's the reason that we look also at geological shortening rates. So there is a lot of work that has been done in the recent years along the frontal Qilian Shan, in the Hoshi corridor. There is much less work that is done, to my knowledge at least, along the southern range here, the Tashi Shan and the Danghenan Shan. So in the following, I want to show you some work we done along the Haiyuan Fault first, on the Hashi Shan here and in this area, and then I will come back to the west. Okay. So this is a view of the Haiyuan Fault which is crossed here by the Wanghe River. You can see here the valley. And this is what we call the Shan restraining band, which is located at the western end of the 1920 Haiyuan magnitude 8 earthquake. The rupture is following this path here along the southern Shan and then towards the east here. And so we work here in the southern Shan. Note already that this range here shows other clear fault branches we will talk about later on. This is a map of this area. You have here the main fault here in the thick line, and you have other faults, parallel, subparallel faults that are also partly left lateral. It's a restraining band, so this you see the change in strike of the fault. It becomes slightly reverse, and so we have a composite displacement here along the strike sea fault. This is a Pleiad EEM. This is topography. Again, you can see very well the fault here along the range, and all these rivers here have deposited these large debris fan here, and as you can see, there are different. From their erosion patterns. Some are standing very high, some are lower and going to the active riverbeds, and they are also left laterally offset. And the good thing here is that we have several of these rivers that have deposited almost the same kind of deposit, so we can play with different sites. These are the view of the different sites here. This is a map of the different terrace level at each of these rivers. And we worked with 4 sites here, and more precisely on one here, this site S1, where we also dated the different terrace levels. So just to focus on this site S1 here, you can see several terraces which are mapped here in these different colors. The source is entrenched here to the north, and so we have a set of offsets that go from about 6 meters to about 200 meters for a set of about 5 terraces. So if we are able to date these terraces, then we can retrieve a slip rate and see how it evolves with time. And we can, because we have not done this dating at all the sites, but we have recognized these different levels at the different sites, we will use the ages of this site to discuss the slip rate at the other sites. This is a view here, just some field view. This is the stream here flowing to the southwest. The fault is somewhere here, and you can see these different levels here from about T1. This is T1, T2, T3, T4, T4 prime, T5. Another view here, taking from the south towards the north. You can see the fault here in the landscape, and the different terraces and the offset that can be measured between the course of the river in the north and the rises here in the south. So at this place, we've done surface and subsurface dating. Just quickly, so on the surface, some blocks have been collected. What you see here is in this diagram are barium on the left and amnium-26 on the right. These are isotope cosmogenic exposure ages. You see here on top of this diagram the surface, the distribution of the surface ages, and below the modeling of the depth profile. We have not done depth profile on all the terraces, so we have 3 terraces dated with the depth profile, and on the other terraces we have only surface ages. The only thing I would just to point quickly is that the distribution of the surface ages versus the modeling of the depth profile doesn't look always the same. Sometimes the surface cobble ages seem to have much more cosmogenic isotopes, so probably a little bit older. Sometimes they are distributed towards younger or older ages, which may indicate that the gravels that have been dated for constraining the depth profile and the surface cobbles have kind of different exposure histories. So when we look at all the data for all the terraces, we can combine the beryllium and the aluminum-26 ages, which are fairly good agreement, and calculate some average ages, which are about 9, 15, 36, and 44,000 years for these terraces. There is some noise in the data here. I can come back to that later if you like. So then we combine the offset of the terraces with these ages. And because we have these 4 sites, we have a set of offsets of all the different terraces at different sites. We use we attribute the ages of the one side to the other side to combine this data and calculate an average or best fitting slip rate for that takes into account all the offsets at all the sites. And so what's come out here is a rate of about 3.1 to 3.3 millimeters per year for this stretch of the Haiyuan fault. So remember the figure at the beginning where I said the fault is not unique. There are several other faults around the Shan restraining band. This value is a little bit small compared to the average long-term slip rates along this fault at this place. And this is probably due to the fact that other faults accommodate the displacement. I will move now towards the west, in the eastern Langnong to the side here, so west of the Jianshu Pula part here, just east of the junction with the Gulong fault. This is the fault that I think the team at IPGP in the tectonic lab of Paul know quite well. Has been published by Yves Godmer and co-authors in 1995. And the famous, what we call the Sangedun site, but it has, we call it now with another name. It shows clearly the Haiyuan fault trace here, and which offsets some terrace riser very clearly. But notice that while some of the rises look quite straight, they are well rounded towards the downstream, towards the south. There is some curvature, and also there is some vertical displacement. So Yongshu went back to this site, made some leveling, and now we have a very precise DEM. This is a slope map here. Again, you can very well recognize the rises here with the shadows or with the steeper slopes here, and the trace of the fault. And you can also see that the fault scarp here is a vertical fault scarp. There is vertical displacement. So with this, we can do or redo a map. This is some of the offset measured in the 90s. This is what we did almost 30 years after. The values of the offset, maybe it's small for you to read, but they're not very different. Again, the offset measurements and the piercing points are not so different than what has been done before. What I think we reinterpret here is that we better emphasize the fact that the top of the riser and the bottom of the riser's offset are very different, due mostly, I think, because of this vertical displacement, and so probably the rises are diachronous in the sense that offset occurred during incision. So just to go quickly with this, here you have some transverse topographic profile that shows you that the fault scarp is also a vertical fault scarp. It's not only horizontal displacement. So what we did here is to constrain the ages of the terraces. There has been some cosmologic ages on the surface, but also here in a pit that I will show here. This pit is a composite pit where you have the base of the conglomerate here, which is the material of the terrace deposited by the river, but on top of it you have this 1 meter 20 soil developed on top of the conglomerate. You have first something which is more sandy, and then you have a big black soil that you can see here in the pit. Some C14 ages have been done here in the lower part of the soil, and some OSL ages in the fine-grained sand here. And these are the ages that are obtained, about 8,000 years for the C14. Okay, I try to go quickly. And some OSL ages. Okay, I wanted to give you some details about the dating techniques. Maybe I will go a little bit faster. And we did some depth profile in the conglomerate. So, well, we model this cover here, which shields the conglomerate in the bottom different ways. What comes up mostly is that we have an age which is well determined at about 14,000 years. So with this, we can compute a long-term slip rate of about 5 to 8 millimeters per year at this site for the Haiyuan fault. So okay, so let me then move quickly. Je suis vraiment en retard. It's okay. Okay, so quickly about the Subay junction. This is a spot image view from 1986, I think. You can recognize the Altyn Tagh fault here clearly. This is the city of Subay, and you can clearly see here that some thrust faults branch into the Altyn Tagh fault. This is a more clearer view. Here again, you can see the trace of the Altyn Tagh fault here that goes to the northeast, and you have these branching thrust faults that uplift here the Eocene or tertiary red beds here. You can see another fault here that runs into here. And so one of the things that we were interested is to constrain the shortening rate here and to try to see the connection with the shortening absorbed here with the slip rate decrease on the Altyn Tagh fault. I will come then back a little bit later about how this transforms here to the east. So quickly, this is the view of the folded and uplifted tertiary red beds that are capped by quaternary, late quaternary conglomerates. Again, same technique. We go on each of these terrace levels. We can measure their height. We can then try to date all these levels. What we did with the depth profile and cosmogenic isotopes. These are a view of the deformation of these terraces. Okay, we can measure the vertical offset. I go a little bit quickly. Okay, here we discuss shortening amounts by discussing a river profile change with time. Okay, dating again with modeling of the upper cover here, depth profile. This upper terrace here, which is about 60 to 100 meters high, is about 128,000 years. Okay, so with this, we get a shortening rate along one of these faults here, what we call F1 here, about 0.5 to 1 millimeter per year of shortening. We don't know still the rate of shortening on these other faults here, which remains part of this discussion. And what you see here in this map is that this thrust fault here, which branches on the Altyn Tagh faults and branches again on secondary or other strike slip faults that propagate into the Qilian Shan towards the northeast. And so, okay, I'm not going into the details, but we have different scenarios here where we discuss how the rate on the Altyn Tagh fault is decreasing, passing these thrust junctions, and depending on how much of shortening we put on these other thrust faults to the south, and there is another one even to the south of the Danghenan Shan. Okay, so okay, past this, I go quickly. If you allow me just to show, I just go quickly. Okay, just to show you this, then I finish, I think. This is the work we are doing now on the Danghenan Shan. So on the Danghenan Shan, we have two active thrusts. Here it's a simplified map of all the different terrace levels. It's the same technique we are applying. We will measure precisely the deformation of these different terrace levels and try to date them. We have here a collection of about 6 depth profile and I think about 150 surface cosmological isotope ages that are now processed to try to constrain the shortening range across the range. This is again what I'm not detailing here. You know the technique. We map this, we level them, and we date them. Okay, always the same story. Voilà. So here we will discuss truss geometries and how the different truss combine to accommodate the total shortening to try to get some shortening rates. So I'm showing this again here. Xu and co-authors that published this came up with this average value here of about 1.5 millimeters per year shortening per 100 kilometer. This is what the geodetic field is indicating on average presently, like in the last 20 years. How this is really accommodated on the long term on the geological time rate. This is what we want to determine. Well, I want to finish and I'll let you read my conclusions. Thank you.